Hi, everyone. I hope you're doing well. Today, we're going to continue learning about special techniques for finding the electric potential by solving Laplace's equation. We've already learned some really important results. We've learned that the solution, that the potential in some charge-free region is uniquely determined by the value of the potential at the boundaries of that region, or by the charge density at the boundaries of that region. In other words, if we can find a solution, a function that solves Laplace's equation and agrees with the boundary conditions of our problem, then we found the unique solution to our problem. So that's the approach. That approach will inform what we're doing today. All right, here, let's take a look at an outline, and then we can talk in more detail. All right, well, so as I mentioned, the method of the uniqueness of the solutions led us to one important technique for solving our problem. We could use the method of images. If we could find some crazy combination of charges which produced a potential that we knew satisfied the boundary conditions for our problem, then we knew that the potential produced by those charges would be the unique solution to our problem. In other words, if we can guess the right answer and show that it agrees at the boundaries of our region, then it's the only right answer that there is. And so we're all done. Well, today we're going to be a little more mathematical and rigorous, but we're still going to look for a general solution that solves Laplace's equation and force it to agree with the boundary conditions of our particular problem to find the solution, the unique potential for our particular problem. Okay? And we'll see how separation of variable works. It's a very general approach. It can be used to attack all sorts of partial differential equations. That's what we're studying right now. And then we'll see how it works in this case, and we'll look at an example system. Today, the examples we look at will all have rectangular symmetry. That is, we can describe them all easily using Cartesian coordinates. Okay? And you'll see that the piece of mathematical structure we developed last time, the Fourier series expansion, will play an important role in finding the solutions to these problems. Okay? Here. Let's take a closer look. So what we're trying to do is to solve this partial differential equation using a technique called separation of variables. And this is a general technique for solving partial differential equations with boundary conditions. It's what are called boundary value problems. And it's used in physics to do all sorts of things, because there are many kind of partial differential equations that turn up. Here are some partial differential equations you might encounter. Okay, well, of course, there's today's topic, Laplace's equation. All right, but here's another one. This is called the three-dimensional wave equation. And it describes classical waves. It says that del squared, or second spatial derivative, of the height of the wave, amplitude of the wave, is equal to 1 over the speed of the wave squared times the second derivative of the amplitude with respect to time. Okay? Any system that satisfies this wave equation will exhibit waves that move at some velocity c. Another one, partial differential equation we're pretty familiar with, is Schrodinger's equation. Okay, which tells us that a constant, h bar squared over 2m, times second spatial derivative of psi can be written as the energy minus the potential energy, times psi. Okay? And the last one would be that I'll talk about today, or mention today, is the heat diffusion equation. That tells me that the diffusion coefficient times del squared T is equal to the first derivative of the temperature with respect to time. You can see all these equations, they look kind of similar, right? And it turns out that their solutions look kind of similar too. Laplace's equation is, and the time-independent Schrodinger equation are unique because they don't have time in them, but all the rest of them have the del operator in them on one side, and then some other combination of terms on the other side. And they can all be attacked using the technique of separation of variables. All right, well, let's stop this video here, and then we'll take up our problem in more detail on the next one.